Hi everyone, today we are going to explain about question 1 of the simulation and credibility theory CBT. So for question 1, assume there are a total of 267 multi-sided dice of which 54 are 4-sided, 44 are 6-sided, X are 8-sided, Y are 10-sided, and 33 are 12-sided. The multi-sided dice with 4 sides have 1, 2, 3, 4 on them. The multi-sided dice with the usual 6 sides have numbers 1 through 6 on them. The multi-sided dice with 8 sides have numbers 1 through 8 on them. The multi-sided dice with 10 sides have numbers 1 through 10 on them. The multi-sided dice with 12 sides have numbers 1 through 12 on them. For a given die, each side has an equal chance of being rolled. A friend of yours has picked at random a multi-sided die. You do not know what sided die he has picked. He then rolled the die and told you the result. The result is a 7. You estimate the result by using two different methods, Bayesian and Bowman approach. The difference between these two estimated values is 0.2150888256. Negative 0.2150888256. Find X and Y. So we are going to use the solver function in Excel to calculate the values of X and Y after linking each cells according to the Bayesian and Bowman formula. I'll start with the Bayesian method for question 1, where the total number of dice is linked over here with the 5 types of dice that is included in the question. For dice with 8 sides and 10 sides, it's initially an unknown before we use the solver method to calculate the value. And then we calculated the probability of rolling a 7 on the die for each dice. So these are the probabilities with the fractions. For the dice with 4 and 6 sides, it's 0 because they don't have side number 7. And then for the total of this column is calculated over here by multiplying it with the proportion, the weightage of the total dice. And then we calculated the probability of each dice given X equals to 7 here by using the formula and the value that we have calculated in cell D5 for all 5 dice. And we obtain the value of the total probability of 1, which indicates that all the probability for each dice has been included in the calculation. Then we calculated the expected value for the second roll, given that they are from each dice that is available. So the formula is by calculating the average of each dice for all 5 dice. And then for Bayesian, the formula is to multiply the expected of the second roll given dice number 4 multiplied by the probability of dice 4 given the first roll is X equals to 7, and add them up for all dice 4, 6, 8, 10, and 12 sides. And then that is the expected value for Bayesian.
So next, I will be explaining the Bowman method for this question for predicting the expected value of next row. So for Bowman method, it requires us to find the expected value of X in condition given the dice is dice 4, and all of the expected value is listed as shown in the screen and is actually the same expected value used in the Bayesian method. And for the variance value that we are required to find actually is very easy. It just needs us to add up all of the value on the dice. So for example, in dice 4, it has the value 1, 2, 3, and 4 in it, and we just need to square the value and divide it by 4 because it all has the same probability to get all of these values, and we just need to deduct the square of the expected value and we will get the value of the variance in condition of dice 4, and we will do the same procedure to all of those dice involved in this question. After getting the expected value and the variance value, we will be getting the expected value of x in condition of dice. So it depends on which condition, and we will add all of those conditions together. And as a whole, we will be times the expected value with the probability given, and we will get the expected value for this. And the second thing we need is the expected value of variance of x on the dice I. So basically, we just need to times the variance value with the probability of getting that specified, and we will be getting this v, which is the expected value of the process variance. So the last thing we need is the variance of the expected value of x on the condition of the dice. So basically, in this value, we just need to find the expected value of x squared on the condition of dice. So basically, we are just taking this table which we name it as 1. So basically, we just take the expected value here and square it, and we just divided it by we just multiply it by the probability. So we will be getting the expected value of x squared on the condition of dice. And after that, we will be just need to deduct this whole value with the mu, which is we have found up here. So we're getting the value of a. And for the value of k, we just need to divide the b with the a. So we'll be getting this value. And for z, the formula for z is actually very easy. It's just the n divided by 1. Actually, it's n divided by n plus k. So basically, n in this question is 1. So we just take 1 over 1 plus k, and we will be getting this z. And after getting the z, we will be able to find the Bowman value. So for the Bowman value actually is z times the x bar plus 1 minus z times the mu. So basically, in this question, the x bar is 7 because the first value that the row got is 7. So basically, we'll get this value. So after formulating the whole formula, which is Bayesian and Bowman like this, and we will be getting the B2, which is Bowman, and the Bayesian, which is B1. And as the question given is B2 minus B1, and it will be equal to negative 0.21508826. So we have these values, and we have the whole formula already in Excel sheet. And after that, we will just be using solver. And we will link the Z objective to this column, which is the B2 minus B1 column. And we will set the value to negative 0.2150888256 as asked in the question. So we would set by changing the variable cells. So this variable cells actually is the x value because it's still an unknown before this. And after that, we just need to click solve. and the solution would be shown on screen automatically, and it would be x equals to 50 and y will be equals to 86. Thank you.